Okay, Algebra 2, we're moving on into 5.7, which is dealing with a concept called the binomial theorem, but we're going to do just a condensed version of it right here and talk about just a little shortcut version of the binomial theorem called Pascal's triangle. The binomial theorem as a whole is pretty cool, but it's really complex and it involves two big skills that we really haven't talked about at all. So we're not going to try to teach them to you right now. Instead, we're going to give you this kind of simplified version right here of Pascal's triangle. Now, Pascal's triangle is named after a mathematician who is French, I believe, named Blaise Pascal, and he came up with this little method right here. What we are doing in Pascal's triangle is we are trying to take a binomial, something of the form a plus b, and then we're taking that binomial to a power, which we're going to call n right now, and we're going to work on expanding that. And Pascal's triangle is a shortcut for how we can do that. Now, what we're going to start writing here isn't going to make a whole lot of sense at first, but I'm going to ask you guys to kind of bear with me. I'm going to draw a series of horizontal lines right here, and for you guys, you probably don't need to do this if you're taking notes on paper that already has lines on it, which I would think most of you are. But I'm going to need this to help me stay a little bit organized here as I'm going through. So I'm going to go, let's see, probably one more and call that good. Okay, here's the way that Pascal's triangle works. The first row of Pascal's triangle, I'm going to put a 1 right there, and that's the only number that goes in that row. Now, there was just one number we wrote there. Each row we go down, we write one more number than what we had previously. So I had one number on my first row. I'm now going to put 2 in my second. And the rules that we follow here, guys, are that we try to center this thing and make it symmetric. The first number and the last number in every row are always going to be 1s. So my first row was just 1, 1. My second row was 2 1s. My third row now is going to have 3 numbers. The first number always has to be a 1. The last number always has to be a 1. And now here's something new we haven't talked about. Any number other than the first or last number has to be the sum of the 2 numbers above it and just off to the side a little bit. So I'm going to add together that 1 and 1 and get a 2 right here. So the third row of Pascal's triangle are the numbers 1, 2, and 1. And now that you get that idea, I'm hoping you guys can figure out where we go from here. The next row, the fourth one, is going to have 4 numbers. Again, the first number always has to be a 1. The last number always has to be a 1. And then, let's see if this works. Yeah, okay, I can add those 2 numbers together, and a 1 plus 2 gets me a 3 for the second number. And then I can add, not that guy. I can add, maybe, there we go, this 2 and this 1 together right here, and that's going to tell me that my third number is going to be a 3 also. So the fourth row of Pascal's triangle is 1, 3, 3, 1. And let's just keep going down. Okay, next row, we start with a 1, we end with a 1. Then I add up the 1 and the 3 here to get a 4. I add the 3 and the 3 to get a 6 in the center, and a 3 plus 1 gets me a 4. So 1, 4, 6, 4, 1 is the fifth row. We're going to go one row further, I think. I'm going to start with a 1. I'm going to end with a 1. I'll add the 1 and the 4 here to get a 5. 4 plus 6 is 10. 6 plus 4 is also 10. 4 plus 1 gets me another 5. Okay, and that is the first 6 rows of Pascal's triangle. Now, as you might be able to infer here, there's no end to this. This triangle could go on infinitely. There's really no point in going a whole lot further, though, and let's talk about what it is that we've accomplished now in each one. First of all, each one of these rows represents a different value here for n. The first row is what would happen if we were to let n, the exponent on your binomial, equal 0. You're not going to use that one very often. And likewise, the second row is what happens when n is 1. You'll see in a second what I mean by all this. And just going down the list, this is where we start using these a little more. N equals 2 and 3 and 4, and then we wrote n equals 5. And as I said, you could keep going on here as long as you wanted to, but I don't think I'm going to give you guys any problems this year that are beyond n equals 5. So what these numbers in blue all represent, you guys, are the coefficients of each of the terms in the expansion of a plus b, a binomial, raised to a particular power. Okay, at this point, I don't expect you guys to have much of a sense for what this is good for, but I am hoping right now you looked at it and you said, okay, I at least understand how the numbers in the triangle were developed. We start with a 1, we end with a 1, and then the numbers in the middle are the sum of the two above it, just a little left and a little right. So what in the world is this good for? All right, let's move on. We're going to do 3 examples here today that hopefully illustrate that concept. We're going to use Pascal's triangle to expand each one of these binomials. So we're going to start off with a relatively simple one, 3x plus 5 squared, but then we'll make it a little harder. Here I've got a binomial to the 3rd power, and then we'll end with a binomial to the 4th power. But let's go back to this first one. I like to start you guys with an example when we learn something new, where actually you don't need the new thing that we just talked about. This is something we already know how to do, and I want to walk through how to do it what I'll call the traditional way. 3x plus 5 quantity squared. The first thing I need to warn you guys about is this. It is one of, seriously, probably the 2 or 3 most common mistakes that Algebra 2 students make, and it's a mistake, don't write this down, to think that you can take this 2 and distribute it backwards into a binomial. A lot of people want to look at this, don't write this down guys, and tell me that the answer is 9x squared. That would be 3x times 3x, and then a plus 25, which is the 5 squared. Let's talk really quickly about why that's not the case. If you guys were to just give me or choose a random value for x right here, let's go with 1, all right? And let's see what happens. I don't think I want that as an ordered pair, but what happens when we put a 1 into this expression right here? Well, just following order of operations, 3 times 1 is 3, plus 5 is 8, and 8 squared is 64. So when I put a 1 into this expression, I got a result of 64 out. Now, if 9x squared plus 25 was correct, we should be able to put the same input value into that expression and get the same output value of 64, if in fact those two expressions are equal. Well, it doesn't work, guys. 1 squared is 1, times 9 is 9, and 9 plus 25 is 34. Not even close to the 64 that I was expecting. So that's just one example here, guys, that shows you that what I did right there with backwards distributing the exponent is not correct. If it were correct, it would work in every single case, but I just found a counterexample. Okay, so the traditional way of doing this, guys, would be to remember that squaring something means to take it and multiply it by itself. 3x plus 5. And now, I'm hoping you recognize what to do here. This is binomial times binomial. We would do FOIL. 3x times 3x is going to get us, 9x squared. The outer product here, 3x times 5, would be 15x. 5 times 3x, the inner product, would also be 15x. Those combine to make a 30x. And then the positive 5 times the other positive 5 would get us a plus 25. And just for fun, when I put a 1 in here, let's see what happens. 1 squared is 1, times 9 is 9. 30 times 1 is 30. So we're at 9 and 30, that's 39. And when we add 25 to 39, that's 64, just like we had right over here before I inconveniently erased that. So this kind of shows you here, guys, it doesn't prove it, but it's strong evidence right here that we've done this one correctly. And in fact, we have. Now, that is not the way we're going to be doing problems within this section, because as soon as I give you something cubed or to the 4th, that's going to become really tedious. So let's talk about how we're supposed to use Pascal's triangle to do an expansion. We are taking now this you should start writing down here, guys. We're taking a binomial here to the 2nd power, and that means that n is equal to 2 in this particular problem. Let's go back to the first slide. N, right up here, guys, is your exponent, and we are looking right here then is what that means. On the 3rd row of Pascal's triangle, where n is 2, we have 3 terms in our answer. 1, 2, and 3, and their coefficients in order are 1, 2, and 1. So let me show you how I'm going to do this. I'm going to write a 1 and then a blank line after that, and then plus a 2, a blank line after that, and then plus another 1 and a blank line after that. There's the 3 terms, and these are the 3 coefficients that we got out of Pascal's triangle in the 3rd row where n was 2. 1, 2, and 1. And now what we do this wasn't explained at all on the first slide, is we're going to take the first term of the binomial, which is 3x, and I'm going to put it in parentheses as a factor right here on the first term. And whatever n is, okay, this power right here, that's the power we put on this first term here. So it's 3x quantity squared. Then each subsequent term gets a 3x factor as well, but that power that was 2 goes down by 1 in each step. So I lower it by 1 now on the second term and get 3x to the first, and then this is maybe a little silly, but I get 3x to the 0 power right there. So my exponents went 2 and then 1 and then 0. And now, let me switch colors. I'm going to go purple here. Now, we take a look at the second term in the binomial, which is 5. And I put a 5 in parentheses right here. And now with the exponents, we do the opposite. We always start with a 0 exponent for what was the second term in the binomial. Then we include the 5 on the second term, but now we increase this power by 1. 0 plus 1 is 1. And then we put a 5 at the end of the last term and increase this power by 1 and get 5 squared. And the one big thing I want you guys to notice, the sum of these exponents, 2 plus 0, is 2. The sum of these exponents, 1 plus 1, is also 2. And the sum of these exponents, 0 plus 2, is also 2. So at every step along the way, I'll erase this because this is getting really messy, but at every step along the way, the sum of your two exponents is always going to be whatever n is. Okay, that's the hard part, guys. Now all we have to do is start simplifying our answer here. So, what are we going to do? Let's see. I'm going to go to, let's go black to finish this one up right here. All right, what's going on here, guys? First thing we should probably talk about is this little mess right here. And one thing that people, well, we say you guys are supposed to know it, but a lot of people forget it. Any number raised to the 0 power is equal to 1. That's probably something you guys should go back on your notes right here and maybe just write yourself a note at the beginning right here, guys, that any number, okay, I'll just put that in parentheses, any number to the 0 power is equal to 1. Let's make sure that we've got that note big and clear at the top of our notes. Now, why is that important? Because right here, 5 to the 0 power is equal to 1. That's going to get multiplied by this 1, and then we have to take 3x and we have to square that. So the 3x quantity squared is going to be a 9x squared. Okay, we multiply that by 1 and 1, and we just end up with 9x squared for the first term in the expansion of this binomial. Then I bring this plus sign straight down here, and now anything to the first power is just equal to whatever the base was itself. 3x to the first power is 3x. 5 to the first power is 5. So 2 times 3x would be 6x, and 6x times 5 would get us 30x. There's our second term. And now bring that second plus sign down and on to the last term. We've got a 1, and then 3x to the 0 power is just equal to 1 again. So this is 1 times 1, and then 5 squared gets us 25. So 1 times 1 times 25 is 25. And that, everybody, is the fully expanded expression right here of 3x plus 5 quantity squared, which you'll notice is exactly the same that we came up with in green here a few minutes ago. And we already checked it by plugging in a 1, and we got a 64 here and here, which means, of course, it would work here also, since these two expressions are identical. So that's how you use Pascal's triangle to expand a binomial raised to a power. And I think it would be a pretty logical question for you guys to ask right now, what method is faster? What we did right here in green or what we did starting right down here? If they both get me the same result, which one should I use? Well, I would agree with what I think you guys are probably thinking right now. This method right here was definitely faster than what we did right over here. So if you ever have a binomial squared, I don't think it's a bad idea at all just to write it out as the binomial times itself and then just do FOIL. But where Pascal's triangle really comes in handy is when you're looking at a problem where the power is something higher than 2. So we're going to do 2 examples right now that show you just how nice and efficient this can be. All right, guys, we're looking at this one here, x minus 3 to the third power. So our n value here is our exponent, and that's going to be 3. So let me go back to the first slide right here, and now I am looking at, let me move my little asterisk, there you go, we're looking right down here on the row where n is equal to 3. It's actually the fourth row of the triangle. And what do I see now? I've got 4 terms. My coefficients are a 1, a 3, and a 1. So here we go, everybody. On the row here where n is equal to 3, 4 terms in my answer. A 1, and then I draw a blank line, plus a 3, and then a blank line, plus another 3. I'm going to try to cram this in here, and then plus a 1, and a blank line there. Made my first ones a little too big. Okay. Let's get some colors going here, guys. All right, my first term of the binomial is x. So I start off with an x right here, and whatever n is, that's the exponent I'm going to put on that first term in the first term of the expansion. So it's x cubed. And then from there, that x power just goes down by 1 each time. So x squared, and then x to the first, and then x to the 0 power. And that takes care of the first term in the binomial. Then, let's see, I think I switched to purple right here. We're now going to work on the second term, but this is a little bit trickier here, guys, than it was on the first one, because you'll notice our second term is now negative, and that's going to make some interesting things happen as we expand this. So I'm not just putting a 3 here, guys. I'm putting a negative 3. That gets started now to the 0 power, and then that power goes up by 1 on each term. So negative 3 to the first power, a negative 3 to the second power, and we end with a negative 3 to the third power. Quick check. Add your exponents together. 3 plus 0 is 3. 2 plus 1, 3. 1 plus 2 is 3, and 0 plus 3 is 3. If that's ever not the case, if those exponents don't add up to your n value, you've done something wrong and you need to go back and fix that. Okay, so easy for me to say, but the hard part is done, guys. Now it's just a question of expansion. 1 times x cubed, that would just be x cubed, and any number, even a negative number, to the 0 power is 1. So 1 times x cubed times 1 is just x cubed. That wasn't that bad. Okay, in the next term now, we've got a 3 times x squared. Well, that's just 3x squared, but now negative 3 to the first power. Remember, any number to the first power is the base, the number itself. So this one's negative 3. So 3 times negative 3 is going to make a negative 9, and then an x squared goes along with that. And that's all you can do with the second term. It was negative because we have a negative number here, negative 3, raised to the first power, which is negative 3. But something interesting happens on the third term. We have a negative number here, 3, and it's being squared. So negative 3 times itself is actually going to give us positive 9. That positive 9 is going to get multiplied by this positive 3 and give us a plus 27. And then right here we just have x to the first power, which is just x. And then on the last term, let's do the hard part first. Negative 3 to the third power. Okay, negative 3 times negative 3 is positive 9, but if we multiply it by another negative 3, that gets us negative 27 times 1, and this is 1 as well. So negative 27 times 1 is a minus 27. And guys, that is our answer here for example B. That's the expansion of x minus 3 to the third power. Okay, so that, I was trying to do a lot of explaining going on in this example here, then showing you other ways to do it, but this was a little more direct. Now that we've gotten into this a little bit, this is what most of your homework is going to look like here. All right, so even though it was to the third power, it wasn't a horrible amount of work. And let's do one more example together here, guys, and I think at that point you've hopefully got it. 2x minus 3y is equal to 4. All right. So where are we right now? Our exponent right there is 4. So n equals 4. And we're going to go back to the triangle now, and we're going to look at the fifth row in this expansion right here of Pascal's triangle. N equals 4. We're going to have 5 terms here, and our coefficients are going to be 1, 4, 6, 5. 4, and 1. So let me get started kind of on the structure right here. So I think I'm going to need 2 rows to do this. You guys can probably fit it all on 1 row on your paper right here. So it's going to be 1 times something plus, we've got a 4 that came next, and then a 6 for the coefficient of the third term. And like I said, keep going if you have room right here. Then a 4, and then a 1 at the end. So those were the coefficients that I got out of the n equals 4 row in Pascal's triangle. 1, 4, 6, 4, 1, and there they are. 1, 4, 6, 4, 1. Always some nice symmetry to that. It ends the same way that it starts. Let's begin with our first term inside the binomial, which is a 2x. So I'm going to put a 2x factor right here, and whatever n is, that's the exponent you put on that first, 2x to the 4th. And then it just goes down by 1 power each term. 2x cubed. We'll then have a 2x squared. How about a regular 2x just to the first power after that? And you really don't need to write it, you guys, if it's to the 0 power, but I like to do it just to be consistent with you guys, and you can see it going down each time. All right, the second term of our binomial is again a negative number, just like it was in the previous example. So I've got to include the negative with the 3y right there, and we always begin to the 0 power. And then that power goes up by 1 each time. Negative 3y to the first, negative 3y squared. Then a negative 3y gets cubed. And lastly, a negative 3y to the 4th power. Okay, let's get working on the expansion here, guys, and see if we can multiply all this out. Okay, what's going on in the first term? I can kind of forget about the 1, and then this negative 3y to the 0 power, that equals 1 as well. So really all I have to worry about is 2x to the 4th. Now, with a monomial base, where the 2 and the x are being multiplied, you do distribute that exponent down there. 2 to the 4th is 16, and then obviously x to the 4th is x to the 4th. And that's it for the first term. Let's move on to the second term now. We've got a 4 right here. 2x quantity cubed. Okay, that 2 cubed, excuse me, is going to get us an 8. And the 8 times the 4 is going to be 32. And then here, negative 3y to the first power is just negative 3y. So I had, what was it, guys? A 4 times an 8, that was 32, and a 32 times a negative 3 is going to get us a negative 96. Then, variables. We have x to the 3rd power here, so that's going to be x cubed, and then y to the 1st power, so that's just going to be a y on that term right there. Okay? Now, I will say, what I did right there, I was able to do in my head, the 32 times 3, but I know I'm getting to the point here where for a lot of you guys, it gets a little uncomfortable to do some of that math mentally. So it will be allowed when we're dealing with big numbers like this for you guys to use your calculators. And I bring that up because I think this third term right here might get a little bit hairy in terms of the numbers that we have to multiply out. Let's see what we've got going on right here, guys. We've got a 6. That's being multiplied by 2 squared. So 2 squared is 4. 4 times 6 is 24. And then we've got this negative 3 squared, which is going to be 9. So what I would probably do if I were you, oh, by the way, can I do that? That's 6 times 4 is 24. 24 times 9, I believe, is 216, but I could be wrong about that. What I would do if I were you guys is I would grab my calculator and I would type the following in. See if you can follow where I'm coming from with this. I'd start with a 6, and I'd multiply that by 2 to the 2nd power. This 2 right here raised to that power. And then I would multiply that by, you'd need to put the negative 3 in parentheses, and that would get squared as well. So I'm going to do that here on the calculator I have right in front of me. Sorry, you guys can't see it. 6 times 2 squared, and then times, in parentheses, negative 3, close the parenthesis, and then square it. Okay, and I got that one right. It was 216. Quick check, positive or negative? We have a negative number right here, but it was taken to an even power. So this third term ends up being a positive 216. And now the variables should be easy. We've got x squared, so that's x squared, and then we have y squared, so that's a y squared for that one right there. Okay, so moving right along, you guys will be allowed to use calculators though when the numbers get a little bit messy. Let's move on into the fourth term. And if I were you guys, what I would type in here is, and I'm looking right here and here and here, this is a 4 times 2. Let me write this at the bottom. 4 times 2. You don't need to put the first power right there. It doesn't accomplish anything. And then multiply that by negative 3 to the third power. Ooh, that's negative 27 times 8, 160, 56. Is that 216 also? I'm going to check. 4 times 2 times negative 3 to the third power. Yeah, that one's also 216. But this one's going to end up being negative because we have a negative number raised to an odd power. So that would be, if you guys have the room, keep going on the same line right here if you can. I'm going to move down a step right here. We're at a minus 216. What do we have there, guys? X to the first power, so that's just x. Y to the third power, so that's a y cubed. And then one last term right here. This one might be a little bit easier. The 1, don't really have to worry about that. And anything to the 0 power is 1, so I can really just ignore that and that. Negative 3 to the fourth power, it's a negative to an even power, so that'll be a plus. 3 to the fourth is 81, and then y to the fourth goes at the end. So that, guys, is as good as it's going to get. That's the 5-term expansion here of 2x minus 3y raised to the fourth power. All right, everybody, that's as much as I was going to walk you through here on section 5.7. Hopefully you guys can dive into that worksheet. You've got a sense for how the triangle was developed and what it's actually useful for, and hopefully you guys are going to do okay on that homework assignment. All right, good luck, everybody.